Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In this session, we are going to go over a new topic, which is line integrals. And if you haven't done that before, basically what we are trying to discuss here is, of course, how to integrate like f of x with respect to x, or double integrals or triple integrals. But in all these cases, um, we were integrating over either the x-axis or the y-axis or both, or triple axis x, y, and z, right? So for example, let's look at, if I tell you what is the integral of a function, just any function. So let's say e to the x dx from, or even indeterminate integral, you know that you are basically, if I say integrating from 1 to 3, it means that I have the equation, or I have the graph of e to the x. So here at 0 you get 1, at 1 you get e, and then this thing is asymptotic with the x-axis, and it goes something like that. We want the integral from x equals 1 to x equals 3, where this is. So we want this area, right? So simply, it's very simple to do. Now, what if I tell you that we have the same function, but it's not dx? I want to integrate it. Instead of this being the base, I have some kind of a graph, and this graph goes something like that. And I have its function, okay? But now I'm integrating an area over a nonlinear straight line. It's not a straight line. It's just any curve, okay? And over this curve, there is a function that increases and decreases, and we want to find the area of that function. Now that's what we call the linear or line integral. Remember that in order to perform the line integrals, some of them are very tough. You will need to use a computer or a calculator to solve them. But the idea is how to set up the problem. Once you have the problem, we really don't care how you solve it. Is it manually with a calculator? But how do you set it properly? Remember in parametric equations, we said, if I want to find the length of this curve, if I have its equation, and we said, okay, let's take a small piece here, dx and dy, and we are going to call that ds, right? And we said, well, we can apply the Pythagorean theorem and say ds square equals dx square plus dy square, and then the right hand, if I want ds, then I'm really taking the square root of that. And then we said, okay, we can multiply inside and outside by dt, meaning we make it a parametric equation. When the dt goes inside, it becomes dt square. So you take the second derivative of x with respect to t, square it, and the second derivative of y with respect to t, and square it, and then I have dt. And of course, I can write this equation as a parametric form, and I integrate. So that's basically to circumvent the problem of having to integrate over a curve. So we will take some examples today to illustrate how we do it. It's very simple. All what we have to do, two steps really, is to find ds in terms of dt, and then parameterize the x and or the y if they are available. So let's take a couple of examples here. We will start with a function. The way we represent the line integrals, we do a line and a letter C that stands for that curve, okay? And let's say here I want to integrate a function that is, let's say x, or let's make it 3x squared minus 4y, for example, ds. And then I have to tell you what is S, the curve, right? So that S is a straight line So S, the curve, is a line joining 2 points, 3, 6 to 1, -1. Oh, I said -1 and I wrote -2. I'm sorry. Okay. Did we learn how to parameterize a straight line? Very simple. Very simple. You say x here can be written as you take the first point, which is 3, and then you look at ending point minus beginning point, you get -2, so minus 2t. And t here goes from 0 to 1. How about the y? The y starts with 6 and then goes down to -1, meaning it drops 7, so minus 7t. Now, let's look at what happens. When you set t equal to 0, you get the original point. When you set the t equals 1, you get 3 minus 2, which is 1, and 6 minus 7, which is -1. Anything in between will move along this line. So that's a straight line going from 3, 6 to 1, -1. So this is the line that we are integrating this function over it. So it's not dx or dy, no, it's an inclined line. So as we said, in order to find ds, we have to take the square root of dx dt, which is -2, and we square it, plus dy dt, dy dt is -7, and we square it, dt. So in order to go from the S universe to the T universe, you're going to say square root of 4 plus 49 dt equals root 53 dt. And it's a constant, the root of 53. Now I'm going to take the integral. Notice we set t equals 1. You could have done anything else, but easiest thing is to use t goes from 0 to 1. You can pick any numbers of your choice and make sure that when I substitute with the lower value, I get 3 and 6. When I substitute with the upper value, I get 1 and -1. So these values would be different. The ds would be different and the integral limits would be different. So for example, if I want to go from 0 to 2, okay, notice you are dropping from 3 to 1, which is drop of 2, right? So I would say 3 minus t, going from 0 to 1. 6 goes to 7, so it has to drop 7, so you have to divide by 2, and you say 6 minus 7/2 of t, and your integral would be from 0 to 2, or any other value, but common sense would say, why make it hard on yourself? Just use 0 and 1. 0 for the initial point, and 1 for the terminal point. Okay, so now I'm going to say it's an integral from 0 to 1, 3, and instead of x squared, I substitute. So I get 3 minus 2t quantity squared minus 4. The y is 6 minus 7t. Everything multiplied by ds, root 53, which is constant, dt. So that becomes my integral. Equals root 53 is a constant. I will have to simplify that. Let's look at, the square term. I have -2t. When you square it, it becomes 4t squared, but it's multiplied by 3, so you get 12t squared. For the t, you have a t term here and a t term there. So twice the first times the second is -12, times 3 is -36, and then you add 28, so it's minus 8t. Again, you can break it down and see for yourself. That's what you will get. And then the constant I have here, 3 square is 9 times 3 is 27 minus 24, so plus 3 dt. Very simple integral. You see, if you try to integrate this with respect, how would you do it? Now parametrizing everything makes life easy. So a constant of 53, And then I'm going to integrate t cube over 3. The 3 with the 12 would make that 4t cube minus t square over 2 would make that minus 4t square plus 3t. And you evaluate from 0 to 1. Of course, evaluating at 0 would give you 0, so you don't need to say top minus bottom. It's just substituting 1. 4 minus 4 cancel each other, and you get the answer is 3 root 53. That's the answer. See how simple it is? Not all integrals would be simple, but definitely it's a way at least to find the answer. Okay, so that's the first example. Let's take another example. And the second example is a 3D. So I'm going to integrate xyz ds. And what is ds? What is the curve s or the curve c that has a length of s? First of all, they are giving you here that in parametric form already. So we can say that r of t is cosine of t, sine of t, and then let's say 2t, whatever, any number. And t goes from 0 to 4 pi. Who knows what is this equation? If you have sine and cosine for the first two, meaning it draws circles, but the t goes up. So as you draw circles, the z goes up. That's a helix. That's a helix. Okay? So we want to find the integration of x times y times z over that helix going from 0 to 4 pi, meaning after two turns of the helix. Wow. Usually without parametrization, you say, how on earth would I do that, right? It turns out to be simple. So let's take, okay. So we are going first to get ds. Notice, now we have three components, x, y, and z. So to find ds, I have to say ds is the square root or of dx dt square plus dy dt square plus dz dt square, meaning, well, I should have said, okay, yeah, dz dt square dt. Well, I know this is a circle, so it's a waste of time. If you take the derivative, square it, and add, these two add up to 1 because you will get negative sine t square plus cosine t square. So they add up to 1. But just to show work, here it is. I'm going to say that dx dt is negative sine of t, but when you square it, it becomes sine square of t. Sine, its derivative is cosine, but when you square it, it becomes cosine square t. That's what I was telling you. These will always add up to 1 if you have the same. So if that's 2 cosine and 2 sine, negative 5 cosine and negative 5 sine, whatever it is, if the numbers are the same, then if they are different, it's an ellipse. But if they are the same, you are getting a circle. Plus the derivative of 2t with respect to t is 2. You square it, you get 4 dt. That becomes root 5 dt. That's it. So now to integrate, I would say the integral from 0 to 4 pi of the following. X, we said x is cosine t. So cos t times sine t times 2t times ds, which is root 5, okay, root 5 dt. Okay, how do I integrate that then? Well, you see here you have 2 sine t cosine t. You should know from the trig identities that this is sine 2t. So here I have root 5 out. It's a constant. The integral of from 0 to 4 pi of t sine of 2t dt. So it became so simple. Here it was x times y times z, but when you parameterize that, you only have one variable to deal up with, which is the t. Now we know that we can use integration by parts. So the easiest way, you do the tabular form. You say you have two functions multiplied. One of them will eventually go to zero. So I will make that's the derivative part, t. And the other one is easy to integrate. In fact, it becomes negative cosine, sine, and so on and so forth, which you will integrate sine of 2t. We are going to take the derivative of t with respect to t, you get 1. Then you take the derivative of 1, you get 0. Once you get 0, you stop. On the other side, on the other side, not sine. I saw sine while I was saying side. I'm sorry. Okay, so when you integrate sine, you get negative cosine. But notice there is a 2, so you have to divide by 2. So it's negative 1/2 cosine of 2t. The integral of cosine is sine, but then you divide by another 2. So the negative 1/2 becomes negative a quarter sine of 2t. And like what you learn, you go from the first entry in the derivative with the second entry with in the integral, and you say plus. Second with third, you say minus. You stop because you reach the 0. Of course, you can keep going and multiply by 0, but who in their right mind would do that? So that becomes root 5 times negative 1/2 t cos 2t, and negative times negative is plus a quarter sine of 2t. And you go from 0 to 4 pi. So root 5, and then I would open two pairs of parentheses with a negative sign between them. I substitute with 4 pi. Okay, I get negative 1/2 times 4 pi times cosine of 8 pi. Any cosine of 2 or 2 pi or multiple of 2 pi is 1, right? So cosine 8 pi would be 1. I also have sine. Sine of 0 or 2 pi or 4 pi is 0. So you get plus 0. And also sine is 0, so you can just get rid of that. Then when you try to subtract, t is 0 already. So whether it's multiplied by 1 or none, you will get 0. And this is 0. So you end up with negative 4 over 2 is 2, 2 root 5 pi. That is the integral. That is the value of the integration. Okay? So that's the second example. Let's take 1/3 so I can show you. Sometimes they give you, let's say you want to integrate x squared y ds, and your curve is the top half of a circle centered at the origin with radius equals 3, going clockwise. Notice in parametric equations, whether you're going clockwise or counterclockwise can make a big difference, okay? Make a difference at least in the sign, positive or negative. But so what we have here, something that looks like that. The curve where you are going to integrate over. So your line starts here. This is the origin. Since the radius is 3, so this point is -3 and 0. You don't need that. And this point is 3 and 0. And you are going in that direction. And on top of that, there is this function that when x is -3, but y is 0, you get 0. But when you move slightly to the right, notice this point would, depends on the angle that it would produce. So that would be cosine, and sine, and then you square the x, you multiply it by the y, you keep going like that, and eventually you go back. So what is this shape? What is the area of that shape of x squared y drawn over that curve, right? Without parametrization, it's probably very hard, or if it's not impossible to do. So let's see what we have. How do we describe this motion parametrically? There are many ways to do it, but one way to do it is to say, okay, I'm going to keep it easy and say x is cosine like we learned and y is sine. You don't have to. You can reverse, but then you have to be careful. If I say I'm going to use x for cosine, when the angle is 0, or if you consider this is 0, okay, meaning you're going, or you can say, well, no, I'm going from uh -pi to -pi/2 to 0, or you can pick whatever value you want. It really doesn't matter as long as you keep track of what you're doing. Okay, so if I say this angle is 0 and I'm moving clockwise, for example, so when x is 0, when the angle is 0, I get -3. Cosine of 0 is 1. So I can say x equals -3 cosine of t. So when t is 0, I get cosine 0 is 1 times -3, so I am here. When t is pi/2, cosine pi/2 is 0, so 0 times -3 is 0, and my x really would be 0. And then when I get to pi, cosine pi is -1, but -1 times -3 is +3, so I get here. And what is the y? Notice if x is cosine, then y is sine. And at t is 0, I get 0. Yeah, sine 0 is 0. And when I get on the top, that's pi/2. Sine pi/2 is 1, but this point is 3. It's 0 and 3. So 3 sine t. And here it is. You're done. That's one way to do it. Okay? I can say this is negative pi, right? And this is 0 and this is positive pi. But since I'm going clockwise, you have to use uh uh you can see how, again, it's really depends on how you want to do it. So here, first of all, I'm going to say ds equals the square root of dx dt square plus dy dt square dt. Dx dt, cosine t is derivative is negative sine t times -3 is +3, so 3 sine t, and dy dt is 3 cos t. So we know that this would be 3, right? Again, it's a waste of time. It's a circle. So ds is just 3 dt. Anyway, it's the square root 9 sine square of t plus 9 cos square of t dt. If I take the 9 out, it goes out as 3. And that leaves me with the square root of sine square plus cosine square, which add up to 1. The square root of 1 is 1, so 3 dt. So now my integral becomes the integral from 0 to pi, because I said here cosine 0 is 1, and I wrote it -3. So I started at t equals 0, like we said. So, and t ended up at pi. Okay, x squared is 9 cos square t, right? That's x squared times y. So times 3 sine t times ds, 3 dt. Take the constant out. I have 9 times 3 is 81. Integral from 0 to pi cos square of t sine t dt. You should know by now, you don't need really to do substitution, but let's do it with substitution, even though I hate that, but okay. Let u equals cos t. So du equals negative sine t dt. Okay? So now my integral becomes the integral. I'm not going to change limits. I will return back to t. You can change the limits and say as t equals 0, cosine t is 1, so the integral is from 1, and when t is pi, this is -1, so the integral from 1 to -1. You can do that. However, I'm going to leave it as if it's an indefinite integral. And I'm going to say, okay, I have 81. Cos of t is u, so when you square it, it's u square. And then I have sine t dt. This is negative sine dt, so I can multiply right and left by -1. So sine t dt is negative du, negative du. It's as simple as that. Then when I integrate u square, I will get u cubed over 3. 81 over 3 is 27, so you get -27 u cubed. Now I'm going to return back and say u was cosine, right? So that becomes -27 cosine cube of t. Evaluated from 0 to pi equals -27 times cosine of pi is -1, and -1 cube is still -1. Minus cosine of 0 is 1, and 1 cube is still 1. So I get -27, -1 minus 1 is -2, equals 54. So it's a positive integral. Okay? So you can see that, of course, we can have problems where this integral is tough to do. You have like a square root of some constants plus terms in t or t square, and there is another term in t outside, and it's not like the outside is not like a multiple of the derivative of the inside, and it becomes really very nasty. In these cases, you are simply allowed to use a calculator and do it there, or a computer. But the way, if you don't know how to set it up properly, your computer won't help you, right? So you have to be careful how we do it. Um, so we took 3 examples. The first one was an easy one. It was over a straight line. Okay. The second one was over a helix, and the function changes the x, the y, the z as we go from 0 to 4 pi, two turns. And then the last one was a top half of a circle, and they tell you it's going clockwise. You can have it counterclockwise. You can have the right half of a circle, 3/4 or whatever. It can be a combination of things. So you can have a straight line followed by half a circle followed by another straight line. In this case, you break it down as if there are three problems and you take each integral separately. It's as simple as that. Okay? I hope this wasn't as bad as you expected. And again, if you have any questions, please leave me a note in the comment section and I will try to get back to you as soon as I can. Otherwise, I wish you all the best and hope to see you soon. Bye.